Nonlinear solution strategy. And the two major topics we're gonna cover is the Newton-Raphson and the modified Newton-Raphson, which is very close to Newton-Raphson. As the name suggests, it is the modified. So the main theme will look like Newton-Raphson, but you have just a minor change. So essentially, if we consider a system of the nonlinear solution and the y-axis is the force quantity, it could be the vector of force. It doesn't need to be just one scalar value, but this is the illustration. This is the visualization of the solution strategy. And another axis is the displacement vector. So what we have learned so far, we set up the equilibrium equations, right? We have the tools that we developed from the beginning of this class. So we will not just drop it off like, oh, that's for linear problem, and now we are gonna solve nonlinear problem. We're gonna make a new tool. Okay, it doesn't make any sense, right? We invest a lot doing all of these infrastructures. So we will solve the nonlinear problem using the linearization techniques, and it is this Newton-Raphson. So how linearization is carried out. So let's see the solution of this problem. It is the response of the system. If you have this much load, then you're gonna have this much displacement, and so on and so forth. The thing is that you can solve the tools that we have. You can solve just the linear system of equations. You have U1, U2, U3, U4, U5 all the way to UN. Then you have n equations. N equations suffice for the solution for n unknown. That's the fundamental. But when your system is nonlinear, so your u might not be just the linear term of u. Alright? You can think about it as like other sort of polynomial terms of u, and so on and so forth. You will need more than just one equation. Just think about you have the terms of the force and displacement relationship. Force given in terms of the square of the displacement. If so, then how many equations do you need? You need more than one, of course. But out of these n equations which come from equilibrium, right, you don't want to dig it out to get more equations to solve. So we linearize it, and the linearization is just start at the very beginning. At the zero load, you know pretty much everything about the structure. At least you have the tangent initial stiffness of the structure. At least you know that the resistance force, internal forces, has to be equal to 0, as you have not applied any displacement. So that is a good starting point. And then we project from this point to the solution point. Okay, so the Here the red line is defined by F star. It is your target, right? It is your force that you apply, externally apply force. The thing is that you have to find the right displacement that balance, that satisfy the equilibrium equations, to balance with that externally applied force. So we start at the very beginning here. Okay. So first of all, at this moment, this u equals to 0 is the initial condition, and the point where you cast the point where you know the information and you cast the equation in order to solve the displacement increment. What we solve in the nonlinear problem using this strategy, we solve for the increment of the displacement, right? So I will write it down in a more specific way than the previous class, but you see it a bit. But this is the current point. So from the current information, what do we get? First of all, we can evaluate current F, maybe the uppercase one. Current F is equals to the forcing function evaluated at u, which is equals to 0. Or if you update your displacement u, you will have the new current condition. Okay. And another thing, your K current, which is also a function that you evaluated at the current u value. So if I generalize it, I just keep the u. Okay, these two are evaluated at a given point. So start at the first step. Basically, I want to solve basically I want to solve and get the displacement increment, which is which is this one here. So displacement increment make it delta u 1. So you consider this tangent line and you get the slope. The slope here is the k initial, k0, so now we are going to solve this linearized subsystem, okay, the first linearization, the first iteration. So this is your residual, if you want to call it, yeah. So force error, it is the force difference from the original, the initial value. Initial value force is 0. So you need to find the displacement to correct this difference from the F star to 0. So this we call the residual. I clean it out. Right. So the residual is equals to the F star minus the force evaluated at current point. The projection will be made from this current point, alright, equal to the K, which is the stiffness matrix, or basically it is the slope of the system. K is the K current as well, multiplied by displacement increment, then I call it delta U. Then just the U without delta, I think it is not as precise as making it delta U, because it is the incremental solution, well, not that, but the increment of the displacement. It is not the absolute displacement, right? It's not the total displacement. So you have this system here, you inverse the K, you multiply by the F star minus F, and as the first step your F current is equals to 0. Okay, so first step you end up with this delta U1. So F star minus 0, that's the left hand side, which is equal to K evaluated at 0, which is K 0, like this. So you know this slope, you know the height here, then you get the delta U1. So that's the linearization, and the first step was done. Then you got to check. The check is carried out. It is possible to do the check because you need to have the constitutive relationship for the member that has the, well, that could be inelastic. So the member that will be inelastic, over here we have the spring, and that is quite a general practice to add the nonlinear spring at the location where the nonlinearity is expected. If you run the finite element analysis, you don't have to do this guess. You just put everything like a solid continuum element, and then all the elements, they have the nonlinear rules that govern the constitutive relationships, right? So you can put the steel constitutive relationship, you put the soil, clay, sand, whatever that we have the information, stuff it into the finite element model. So the algorithm will check the current response that you have, which is associated with the current state of the strain or state of displacement, right? So that means now you know you update. Let's put it here. So the displacement U1 is the update of the 0 plus 0 is from the current, right? Plus the increment we obtain here. So it is equal to basically delta U1. So this will be the new current. Information. Because once you know the displacement, then you know the information about this point. So this point become a new current point. And as it is a new current point, you get the following informations. You'll be able to evaluate the K. It's gonna be the new one. K1. You evaluate not only just the K, you also find out the current force. This one was evaluated from the U1. And once you evaluate this, you check with the F star. And see if this new current information match with the F star or not. If it doesn't match, that means you still have this gap that we call residual. So if residual is still there, we need to keep iterating until we get the converged solution. So if this is not equal, that means not converge. If it is, then you get the convergence. And this procedure is a convergence check, one way. And you're gonna need the convergence criteria. That you can establish. We come to the second step. So you solve the second step using this one, which is the residual is equal to the F star still minus F evaluated at U1. This is your residual, your new residual, equal to K1 times delta U2. So the line is coming down this way. Delta U2 should be just using and make it the vector. Done. Then update. And then obtain the new current. Then the new current is F at U2 be noted that U2 is equal to U1 plus delta U2, that is equal to 0 as the original current plus delta U1 plus delta U2. So that's the newest force. Then do the shooting again, and we use the K which is evaluated at this red dot, and that's K2. Make it like this. So can call this point U1, this point U2. Okay. Once done, again the first thing that you do is to check the convergence. So you go get the F at U3. Basically point here should use this color, sorry. Point number 3. And in here it is delta U3. Okay, and that is the U3. So you update, right? You get the solution, you get the new solution, you get the new current point U3. Evaluate force, internal force F3. See if you balance it with the externally applied force or not, and keep continuing it this way until you get the small enough F star minus F of the U current. So I don't know which step you need to take, but okay, I just say that it is the U current, and then F star minus F at the first step, which is the U 0 or 0 basically, and see if this is satisfying the convergence criteria or not. So basically this one is the definition is the current residual, and the other line is the original residual. It has to be less than some number. And told you last time that this error will accumulate. So if you minimize the error, then when your analysis is long, like you do the nonlinear time history analysis, which is dynamic, and when you do dynamic, you need to also do the time discretization. The time discretization is like you have 2 minutes of the ground motion. You cannot solve in using one system of equation to get the response of the structure over 2 minutes. Again, the time, it is discretized. So you have many equations for each time step. You satisfy the equilibrium, okay, sets of equilibrium equation at a given time step. Once you satisfy that, you use that current in time, okay, current information in time domain, and that will be used to solve the next step information. So 2 minutes could be chopped down into the time stepping size of probably like 5 milliseconds or smaller. So you have a bunch of time step. That means a bunch of equilibrium equation. And if you have the nonlinear system, if you solve at the maybe 10 seconds and the nonlinearity came in, if it is not converged that well, then you keep the residual, accumulate it over, so your solution deviates from the reality. So you need to just emphasize on that. And moreover, if your domain, if your system is quite large, how to say, it's large in terms of the relative size within the problem. You have one problem. It doesn't need to be just the structural analysis problem, frame plus, it could be the finite element problem. Okay, so I just draw the potato like this, and you solve the nonlinear system, and nonlinearity could be just at that corner, which is very small compared to the whole domain. That element might be just, if you have 1,000 elements, you might have nonlinearity only just over a few. That's just example of how I said big. So as the number of nodes or the elements that suffer from nonlinearity is small, when you check the convergence criteria, the overall structure might converge. You have the elastic part, which is like 99%. Inelastic part is so small, so it looks like you get the convergence because the influence of the other parts just dominate. So you can set up more than one convergence criteria. It is just your rule. There is no written formal procedure that you have to just use this or use that. Convergence criteria, there are many criteria. Sometimes people use energy, sometimes you just use this force residual, sometimes you look at displacement convergence, so many. But that's just the way you check the correctness of your solution. So you can set up another criteria. The first criteria might be considering the overall structure. Then the second criteria, you can look at specific elements that you suspect the nonlinearities. You might turn on nonlinearities over a few, then you set another criteria over there. So you not only satisfy the overall, you have to satisfy the local. And if you get these two conditions satisfied, then you let it go. You accept the convergence. If you do not have any of that, you satisfy the overall structure, but locally it's not converged yet, then you keep iterating until you get the all criteria satisfied. Right? So the less the better, but the thing is that it is upon your judgment. You can set the very, very small, like 1 in a million, 1 in a trillion. Possible. You can do that. The point is that if you have 3 steps for 1 in 10,000, and it turns out to be 5 steps for 1 in a million, that's the cost. The computer time is a cost. You feel like structural analysis has no course, which is wrong. Structural analysis has a course. If you feel there is no course, well, that's because you deal with small problems. So you click and then analysis just took you a few seconds. But you are here, you'll be making the high-rise building model in the next semester, probably in the tall building class or high-rise, yeah, Dr. Navid class. So the model is large, 40, 50-story building. You have many elements, and you will not run the static analysis. Okay. If you came here for master in structural engineering and then you do only just static linear analysis, then okay, value added is you don't have, you don't get the value added. You are here to be able to conduct more difficult analysis, and that is not just the learning of the program, as I used to mention. You learn how to use program, but how could you be sure about the response, the result from the program? That is another value added. Being able to use the program, okay, yeah, watch YouTube. And being able to understand the result and check the correctness of the result, that's another jump. So, nonlinear time history. This is the nonlinear step. For the time history analysis, you could have like, just get that idea. 2 minutes, probably. The ground motion comes checked seriously for probably 30 seconds, but you might have like a pre-earthquake and post-earthquake that you only have smaller waves, whatever. 2 minutes is 120 second. 120 second, okay, let's just round it up, just make it 100 to make life easy. And for each time step, if you use the big time step, resolution of the accuracy will not be good anyway. So smaller time step will ensure the correctness of the solution. There will be many criteria to judge, to use, to specify the time stepping size. That will be in finite element course. But let's see if it is like 5 milliseconds, 0.005, 5 milliseconds, 1, 2, 3, and then divide by 5. Okay, you end up with 20,000 steps, time steps. 20,000 multiplied by 3 or 20,000 multiplied by 5. That makes, if multiplied by 5, then you end up with 100,000. Your building is 40-story. So that 40-story building, which includes thousands of degree of freedom, that means thousands of system of equations. Equation associated with DOF. You have that many thousand DOF, that many thousand equations. So you pack all of them into one system of equation and then you solve. And that means you solve the entire system of 40-story building in order to get one iteration, only one iteration, and that iteration is within one time step. Okay, so out of these 100,000 iterations, every time you solve the whole 40-story building, you're done, and then you solve it again, and you're done, you solve it again, and again and again. So it's gonna take you about 1 or 2 weeks if you do the thesis like that, that run the nonlinear time history of a high-rise buildings. It could take you approximately a week. If you have the element like layer shell element, something that pick up the nonlinearity of shear wall, then if the rule is more complicated, the nonlinearity is complicated, that it takes time. For the convergence, it takes time to run the calculation. You just leave that computer for 1 or 2 weeks, and then you come back again. Well, the first nightmare is that the wrong input, and then you waste 2 weeks completely. Wrong input. And don't try to fool us, because when you present your final paper, final defense, you show your response, and you think that you did it wrong, but if you just show the plot, show the graph, and nobody is going to know, there's a way to detect what was wrong in your work. And you were presenting your work in front of at least 3 lecturers who taught you and who has more than 10 years experience in checking people's work, more than 100 work that were checked already. So you cannot just run away or fool around, right? So you got to repeat your calculation. That's the nightmare. You might be about 4 weeks before the deadline of the defense, and then you waste 2 weeks because you. So that's sort of nightmare for you. But this is the course. The very obvious course is that it might just push you through the graduation deadline. That's the first course. And the next course in your life is when you work, when you practice. So when you practice, 2 weeks seems to be quite long to run the analysis and design the building. Your client generally want to rush and get the design drawing very soon, in very short time. So computer time is your cost. 1 week, 2 weeks, 3 weeks. That's up to your decision making in the time stepping size, in the convergence criteria. So balance it. As you are engineer. But if you are not an engineer, you know, okay, this is the best. I'm gonna make like Pico 1 in 10 million error. Whoever can do that. But is that a good balance? You might be out of job to get that high accuracy. Right? There is also like research level work and practicing engineering level work also. So just balance. When you practice, error could be some number, and you know that you have the load factor that will cover you up if it is not too much, if it is not the large error that is detrimental. Well, we can look at this. So just in case you bump into other kinds of nonlinear behavior, because you have seen this, the curve that looks like a parabolic curve. What if we have multilinear? It doesn't allow this. Got to be here. Okay. How about this one? No matter what kind of nonlinearities the algorithm we look at, we study, will work. So let me set this up. If this is the F star, so for this given system you have the trilinear behavior. For bilinear, you might think of steel. Pre-yielding and post-yielding, you get the flat slope. Actually, you have the strain hardening, you have the other things coming later, but generally, the yielding is very large already, and if you pass the yield plateau, your structure is not in the usable condition anymore. So the analysis to the level of strain hardening or ultimate condition is quite rare. It is just in the research purpose in general. So as this one is trilinear, we start again. Okay, so we have the first slope. Pick up the first slope K what? 0. Then turns out you get this solution, you evaluate this solution, and you find that your force is not matching with the applied force. So you run for the second iteration, which goes from here. And then this part, if you call it K1, you'll be getting this solution. And this last one is also the straight line. So call K2, and then you'll be getting the solution without error. So as I mentioned, if you have bilinear, you need just 2 steps, no more. Trilinear, no more than 3. You might use 1, you might use 2, but you will not go up to 3. And the thing is that as the portion is linear, okay, each portion is linear, then you draw the line along the response, the actual behavior, right? The green line and the red line are right on the same, right below the green, or the red is like below another. Exactly. So there is no room for error. But if it is the curve like that, if you keep zooming in, use the electron microscope to zoom in this region, you still find the error. But it is so small and we just accept it. But unlike the linear, multilinear relationship that you will just address to the solution, just hit the solution without any further residual. maybe we can also look at the different behavior if we don't do the behavior we illustrated previously are mostly the softening. Softening, well, definition is basically you have high stiffness at the beginning, and then as your displacement is larger and larger, your stiffness decreases with displacement. In general, you expect the softening. For steel, you have strain hardening. After you plateau that you have zero stiffness, then at one point it pick up. The stiffness pick up, so that's the hardening. But most of the material, as you apply more deformation, as you have more strain, it tends to fail, right? It tends to lose the capacity. So you expect softening, but also hardening could be the case. So what if we have this one, and applied force is that? Let's see how we solve this problem. I will just draw it like a schematic way to understand it, but if we put everything into the procedures I showed you last time, then I'm going to show it by the different problem this time. So you just follow the procedures. You have the correction of the force, the sign might be changed, fine, but you will keep updating your solution, iterating until you get solution. So procedure is the same, but the illustration or visualization here looks different from before. But I'm going to show that it is exactly the same way we approach. So first, you solve this problem. Wait. The picture has to be bigger. Maybe I use this one. Run out of the space, and this line, and I need this load. Okay, and I just draw the tangent like this. Okay, so using the initial stiffness K0, to find the displacement corresponding to the F star, get that, and what do we call it? Is the delta U1. From this delta U1, you update your U1, and that is equals to delta U1. So this point is U1, and you project this up, and you found that this is the corresponding force F for U1 evaluated at U1. Now, how to go to the next step? We evaluate, we construct everything based on the current condition. So first of all, the slope, tangent slope has to be okay. What is the error? What is the residual? Residual is here. Oh. So residual is the F star minus F evaluated at U1. Well, the residual term this time will be negative. And then you have the K1 evaluated at this point here. So, what you solve is this one, right? Sorry. Because the residual for the not much space, F star minus F U1 have no space. So your delta U2 is given there. The new current U2 is equals to delta U1 plus delta U2, but the delta U2 is negative, right? So it comes back to here, and here is your U2. Okay, U1 is positive, U2 as it is negative, so it runs backward. The correction goes back to the left. And then you have the new current point, so you come and evaluate it. For the K2 and F at U2, at the point there, and you find that the error is still there. you're not happy yet. So this new one is the F star minus F U2, and you're gonna draw the tangent line just like that. So you solve. Seems like we can achieve the convergence in this step, delta U3. So you update the current so U2 plus delta U3. Again, the delta U3 as the residual is negative, stiffness is always positive. So you solve, you get the negative U, delta U. So you run backward again, and then you come up with the U3, which is this point where you get the convergence, and then you decide to stop. So softening, hardening, you can make use of this technique. The problem that you might encounter when you use the Newton-Raphson and modify Newton-Raphson, especially for Newton-Raphson, is when your slope is equal to 0. So the softening all the way to the 0 slope, if the overall structure hit that 0 slope, then you will be in trouble. But if some part of your structure hit the 0 slope, but you have the contribution from other members that help pick up the load after one member sort of fail, then you will not get the real system 0 slope. Yeah, for example, the spring I showed you last time, the beam and spring, if the spring is like elastic, perfectly plastic, so the second part is flat, 0 slope, that system is still not having the 0 stiffness, because the stiffness contribution from the beam will work, will carry it out after the spring yield. So that is not the real 0 slope. The 0 slope has to be the overall system 0 slope or 0 stiffness, and then the problem will come. So this structure, I'll just make it simple for calculation. So this is just EI 2 EI and 1 L, EI and L. The load, distributed load W is equal to something EI over L cube multiplied by the factor, which is, well, make it 0.1. And then we have spring. I will make the rotational spring behavior like bilinear. Elastic, perfectly plastic might work. And the vertical spring should be sort of polynomial. So let's work on this behavior together. K, the vertical spring, well, make it the same. So KT translation, should it K? No, I make it, I name it spring T. Okay, translational spring, and this is the spring R, rotational spring. So for the spring T, this is the force and the deformation. Okay, keep it U. Behavior could be just like this. First part is linear, and you have a smooth transition after this point. Okay, the linear part is up to if we want to make sure that it yield, I put high stiffness but low yield force, it will yield, right? If you have low stiffness and low yield, maybe it doesn't yield. High stiffness, that means small deformation, it mobilizes the load very quickly. And then that load mobilization, which is so quick, hit the yield force. So it doesn't take large deformation. If you have low stiffness system, you need large yield in order to reach to that yield force. So yeah, I just want to make sure that it yield. Then I should make large stiffness and low yield. So stiffness, initial stiffness should be you have two springs. Okay, maybe one of them might not yield, or well, they could yield both. 50. Over L cube. So this linear stiffness is just, and then regarding the force, I'm pretty sure that W times L approximately, this is just an approximate way to look at the problem. W times L, which is like in this tributary area. In reality, it could be like 1.2 or 0.8 WL. The number will be that in that vicinity. So approximately 1 WL. 1 WL is equal to 0.1 EI over L square. 1 WL. This is W, so multiply by L, then you get 0.1 EI over L square. So I make this, I want to make sure that it yield, because we are teaching nonlinearities. If the system is elastic, ridiculous. 0.1, right? 0.1, make it 0.05, have a wonderful yielding. 0.05 EI over L square. So it's the first yield force, because why? No, this is about 1L. 1L multiplied by W, I get 0.1 EI over L square. And then that is the expected reaction in the spring, rough estimation. But I want to really make sure that it will yield, so I just half the capacity down, so it should be lower than the reaction force there. So yeah, I said it 0.05. If it doesn't yield, then later on we come back and then lower it down. But if it is very low, I just don't like too low value, because that curve will take over the whole thing, and that curve has low stiffness, so deformation will be super large, but it might look ridiculous. So in order to obtain this curve, we know the point here, the equation has to pass this point. Actually, this is not your business, it is my business to do this thing, because when I make problem, when I make exam, then I have to figure this out. But okay, I just showed you. So to find the corresponding yield displacement, 0.05 will be divided by 50. 0.05, which is the force, divided by 50. EI cancel out, and you have just the L. And then 5 cancel, you get 1. This is 10. So it is 001, 001. Okay. Double 001 L. And the slope at this given point has to be 50. So I'll figure out the equation. Oh well, the equation has to be in the form that makes the y equals to, you're gonna have ax squared plus bx plus c. If I want to make it parabolic, if it is a parabolic curve, how many points you need to solve to obtain the A, the B, and the C? You need 2 points and 1 slope condition, or you might need 3 points. Basically, you need 3 equations. Over here, we have the slope that has to be 2ax plus b has to be equals to 50, right? Initial slope was 50 EI over L square. So if the y prime is 50, evaluated at x or u, okay, it should be the u, right? Inconsistent. Fine, just understand that it's gonna be the x. So substitute the 0.001 L in there, and then you will get 50 EI over L square. L cube. So 2a multiplied by 0.001 L plus b equals to 50 EI over L cube, the first equation. Second equation, y evaluated at 0.001 L is equals to a times 0.001 L square plus b 0.001 L plus c equal to 0.05 EI over L square, 0.05 EI over L square. Equation number 2. Parabolic, you have 3 unknowns. So another point, it will be just sort of arbitrary point I pick up here. Well, let's see. If this is 001L, I guess somewhere here might be a nice place to 001, 002, 003. Okay. So around 0.003L, this is 50 and this is 0.75 EI. Zero point 0.075 EI over L square. Cannot. Okay. Okay. And food. Okay, 003 correspond to 0.75. Actually, I don't intend to keep this in the note. It's just like a scratch paper for me. But if it is going to be kept in the note, let me make it right. A u square plus b u plus c and what should that was supposed to be the y, and that df du, which is evaluated at u equals to 0.001 L, is equal to 2au plus b, which is 2a 0.001 L plus b, which is equal to the slope 50 EI L cube, and that is equation number 1. And the number 2 was f at point O1L is equal to a point O1L square. Sorry, this is not right. Square outside plus B point O1L plus C equals to 0.05 EI over L square. Yeah, I can cut this point out from the video when I made the first scratch paper. And the last one, f at 0.003L equals to a O3L square plus B 0.003L plus C equals to 0.075 EI L square. But again, when you do exam, this will be given. You don't have to make this. It is my job to make it for you. So ABC solved, right? Basically, for equation number 1, if you multiply through by L, if you multiply through by L, you get L square, not the whole bracket square, just L square, and BL, and this turns out to be 2. So equation 1 and 2 and 3, they are basically pretty much the same. I mean the magnitude of the L, the power of L, are the same, uniform throughout. So we'll just do this 0.002 L square. I will produce the matrix form of these sets of equation for 3, 0. This is taken from here. For A is 0.002, for B is equals to 1L, for C is equals to 0. Second equation, for A it is 0.001L, the whole thing square. For B it is 0.001L. For C is equal to 1. Alright, you get a matrix format. And you have the A, you have the B, you have the C. I will make it AL square, I will make it BL. So the L is no longer there. But square has to be there. Here also, L's gone. So you can put this in Excel if you want. Well, you don't want to again because it is my job. equal to right hand side 50, 0.05 and 0.075. These are all multiplied by EI over L square. And then if I solve, everything will be in terms, the A, B and C will be in terms of EI over L square. For time being, I just set this matrix up in my Excel scratch pad. 0.002 1. I may not hook it up for you. You can just do it yourself. 0.001 square, 0.001 and 1, 0.003 and 0.003 square up, and then on the right hand side we get 50, we get 0.05 and 0.075 right hand side. I will inverse this matrix in order to get all these A, B and C, and we'll write that down. MMULT of M inverse of that matrix, and then linear equation be solved, and we get now next page. Okay, I got A equals to minus 18,750, B equals to 87.5, and C is minus 0.01875. So essentially your A is equal to minus 18750 EI over L to the fourth. B is equals to 87.5 EI L cubed, right? And then the C is equals to that 0.1875 EI over L square. And that makes the equation for F equal to minus U square over L square, U over L square, plus 87.5 U over L minus 0.01875 with nothing, and we break it up. EI. So this is the equation that governs your spring. or the spring actually it is a translational spring constitutive relationship. So both springs are just like this one. Regarding the SR, the spring that restrain the rotation, I'll be putting the bilinear. Actually it is elastic perfectly plastic relationship. And we are talking about the moment and rotation relationship. If you don't know this one, this is called elastic perfectly plastic behavior. And that's something like steel. You pull the steel, stress-strain relationship for steel is elastic perfectly plastic. If you have the force and displacement, it will behave like elastic perfectly plastic as well. If you get the steel beam, steel cross section, which is like a Y flange, H beam, I flange, under moment, your moment versus rotation is gonna look pretty much like this. This is not a steel class, so we'll not talk about that, but you will get the behavior which is pretty much like this, but you have just this slope a little bit, and that is how you can draw the curvature and make the moment curvature response, which is really fun. Actually, when we code the octave, let's make it moment curvature relationship for all kinds of things: concrete, RC, steel structure. Actually, I used to code this thing in Excel, but Excel, the looping, the iterative solution is difficult. It's not automatic, but it's still manual. Okay, I can do the Visual Basic, but Visual Basic is not my favorite. So I better do it in Octave or MATLAB. Oh, alright, but that's not relevant to what we are focusing. We will be back in here. So the slope is 40 IRL, that's stiffness. make it almost like the fixed end, make it 100 EI over L for the slope. And you know, if the stiffness of the spring is really large, so it mobilizes the moment very quickly. Let's see how much moment at the right hand side we expect. Normally, if it is a fixed support without spring, without anything, it's WL square over 12. This is 2L, so W 4L square over 12. So let me scratch 0.1 L, which is 4, W 4L square over 12. L square cancel out, 4 to 3, so that's a 0.0333 EI over L, and that is expected if it is rigid. So I make it weaker, 0. It's just O3 or okay, O3, huh? 1 over 3 has to be 0.0333, yeah. So 0.01 EI over L. Huh? Just L? Yes, okay. Because the rotation is dimensionless, so slope and the moment are having the same EI over L. I'll clean this point up. And what is the corresponding? So this is pretty much like the plastic moment of your RC beam. You form the plastic hinge. Once you exceed this deformation, and that is why ACI emphasize you when you look at the chapter that talks about the strength reduction factor phi. Strength reduction factor phi is 0.9 for the flexural member. Is that what you understand? Yes. Which actually you just take a part of the provision and then you just memorize one part of the provision. It doesn't say anything that it is for flexural member. It said that if your member, whatever, will undergo the tensile strain up to about 5,000 microstrain, or the latest one, the latest most is the 31819 issued this year. So it gives you more, so not just 5,000 microstrain. 5,000 microstrain is the 0.005 that you see. So it was increased to 0.0055. So it is 5,500 microstrain. So if your structure will be able to sustain the large deformation and your steel will undergo to 5,500 microstrain of tension, of tensile strain, you are allowed to use the phi reduction factor equals to 0.5. The thing is that when you design the flexure, when you design the beam, do you check if your beam or your reinforcement will go up to that far? I guess many did not. So you just design the beam, you get some reinforcement, then oh, there you go, use it, and use 0.5. It's 0.9, sorry. So 0.9 is for the ductile failure mode. And if you cannot achieve this level of tensile strain, the transition equation was provided. So it's reverse. So this is a strain, 0.0055. This is 0.0 something, don't remember. And this is the phi value. So 0.9 is this point. If you are beyond 0.0055, that's up to you. More ductile, but you cannot gain more phi. But if you can get less than this 5500 microstrain, then you need to adjust the phi factor by this equation. This line is given in the code already. So it could be 0.85, it could be less than that, all the way up to 0.65 when your structure is is compression control. So that's the thing. You better use things with some fundamental understanding of it. So if you understand this already, good. If you just use 0.9 and memorize that 0.9 is for flexure, sometimes you design the beam and you really cannot get the 0055 because it is heavily reinforced. The coupling beam in the wall, many times that you stuff too many reinforcement there. No, you cannot mobilize high tensile yielding strain. Okay? Reduce then if you bumped into that situation. Okay, so you get the plastic hinge formation. Behavior is exactly like this, and then bilinear. So if we find the corresponding yield rotation, you divide this by EI over L, so O1 divided by 100. You put 2 more 0. So that makes 0.1231 radian. Dimensionless. Now, I finished my business. It turns out to be your business from this point on, after I figure out the how the configuration of the problem should be for the governing equation for the spring and the rotational spring and the translational spring. So we'll perform the analysis. Let's first start with the definition of the DOF. So for this problem, for DOF, at the left support, we use the row column elimination. Let's continue here. So we're gonna solve iterative solution. We will use Newton-Raphson. So I put it here, Newton-Raphson. We can do modify Newton-Raphson in the same file, but we're gonna make a new sheet. We can copy this sheet and use the different nonlinear solution strategy. So here I paste the pictures of the problem over here. We will have 4 degrees of freedom. We involve 2 beam elements. These 2 beam elements are not going to be inelastic. All right, it is just the linear element, but the nonlinear elements are only 2 translational spring and 1 rotational spring. So let's solve, but we need to prepare the infrastructure like this a little bit for the beam. So left beam, you're gonna have the right beams there. Left beam, boop. Okay. 2 EI and 1 L. So I'll go through this quickly. 12 EI over L cube equals to and equals to. Alright, and then 6 equals to 6 times EI over L square equal to this one, equal to this one, equal to this one, and equal to minus of this, equals to this, equals to this, and equal to this. 4 and 2, right? Equal to 4 times EI over L equals to 2 times EI over L, and that is going to be this one, and here this one. And that scale by will be multiplied by U1, U2, U3, U4. The top equation will be multiplied by the L to make it like moment equation, and later on we take the over L outside as usual. So we have the EI over L square, right? Out there. Right, EI over L square. EI over L. Huh? If you multiply through, then over L square, then we L square L, and then take this small out, then it's all over L. Okay. EI over L, like that. Multiply by the displacement unknowns, and the right beam will be the same. So there you go. But the right beam you have 1 EI, and your right beam, this is for U3, for U4, for U5, and for U6. This problem includes only 6 degrees of freedom, but now we have left translational spring. Basically, I think better make like a ID for the spring. Okay, you can be sloppy a bit here. So for the translational spring, the spring behavior, how would I say, the current condition of the spring. So we have current, force, and current translational stiffness will be given over here. So for the force, I'll merge and so for the force, remember EI over L square, EI over L square, and stiffness is over L cube. These are the function of the current displacement, which is in terms of L. So at the very beginning you have 0 L. Force is equal to what? Get the equation. Equation is in the here. We have minus 18750 multiplied by U over L square. So it is this term ABS of this one square plus in the force expression I wrote in the PDF, please add the denominator L square. I wrote FU equals to EI, and then in the bracket 18750 U over L all square. Things in the bracket are dimensionless, so the scale outside has to be EI over L square. Alright, please add the L square as the denominator to make it correct, consistent in the unit. 87.5 times absolute value of this one. So this spring will work for both tension and compression, and minus 0.01875. There you go. Did I? Current force. Why is it minus? It was supposed to be 0. Huh? 0, 0. Oh, okay. There are two rules. If the displacement U is less than or equal to what is that displacement? 0.001. Then the force will be evaluated by 50 multiplied by the absolute of this, but then it will be nonlinear, so I need to put this absolute value as well. It is nonlinear, right? So it is governed by two pieces of curves. The first is the straight line. When you have small displacement, system is still linear elastic. And when you exceed that limit or the yielding occur, you come across to the parabolic curve, and then that complicated equation takes over the behavior, the constitutive relationship. So okay, turns out to be 0. If I just put small one in here, 0.0005, then okay, that is equal to 0. And how about the stiffness? The stiffness, I will use this, and no, okay, I use this. And put in here, I just need to use the condition there. But for the stiffness, it will be equal to 50, right? If it is not U. And it will be equal to 2AU plus B. So this is A times 2 times U, which is not square, plus B. That's it. And enter. So you get 50. So things are quite systematic. This is the left translational spring. We put the right translational spring somewhere there. And well, they work in the same way. Likewise. And the rotational spring. Current theta. Current moment, current spring stiffness, theta no unit, moment this unit, and stiffness this unit. The thing is that the theta is whatever the m. When the theta is saturated, the moment is equals to 0.01. If it's not saturated yet, it is 100. EIOL multiplied by theta, and the theta limit is 0001 radian. Okay, and here 0, 100, 0001. Okay, 100 EI over L slope when the spring is elastic. When it turns plastic, you have 0 stiffness from the spring. So moment still saturate. The cross section still resists the moment at that cap value of 0.01 EI over L. Moment doesn't drop. The only thing that drops is the stiffness. Okay, 0 stiffness, but moment is maintained. This is favorable for us. This is the place where energy dissipation occur. For earthquake engineering, this is great. And this is how what we talk about ductility of the structure. So if the structure is ductile, then it can sustain this zero stiffness, but moment is maintained for long. So ductility ratio like 4, like 5, that would be cool, because 4 times or 5 times of the U displacement, it can maintain that MP for that long. If the structure is failed by other mode of failure, it go up, maybe reach the MP and then a bit drop. This is not good. So it doesn't carry this load anymore, then the load will be redistributed to other member. Okay, so the more ductile the member is, the more energy dissipation, the more likelihood that your structure will still stands up. But maybe the beam develop plastic hinge under the lateral load and it can go for long. But you might have the other killer that come into the picture. The other killer is the nonlinear geometry. So second order effect, your building sway too much. Even though the plastic hinge formation occurs, your structure is ductile, but the deflection or the drift is not controlled. Horizontal drift is not controlled. The part that will bring your structure down will be second order effect, because lateral drift is large, your force gravity load is huge, and the larger the lateral drift you have, the more moment, and that will bring everything down. So for large deformation analysis, for large deformation which is caused by the earthquake, you really need to turn on nonlinear geometry analysis to incorporate that P delta that bring your column down. If you don't turn that on, then you just make your structure ductile and you don't care about second order effects. So structure will just go 5% drift, 8% drift, still there. It's still there in your computer. The real one might come down at about just 2 or 3%. Yeah, some tips about things that might not be just this class. So everything is construct, and then I construct the 4x4 matrix system. Just system of equilibrium equations, and that includes this. Zero it out. The number is gonna be small. No, stiffness is okay. So U3, U4, U5, U6 will be there. This part is equal to this plus this one. Boop. Boop. This is equals to this one. And then I plug in the spring stiffness. I think I shut it out and one step down. So I plug in spring stiffness. The spring, translational spring on the left is at U3. And another translational spring on the right is at U5. And we have rotational spring at U6. Yeah, everything is in there. So this right hand side of the equation, the K and the U were all there. Let's take a look at the fixed and reaction. Fixed and reactions. So that is equal to W, which is 0.1 times L, which is L over 2, WL over 2.5, which is equals to this one. And this is EI over L square. And this one is the moment. So this is equals to W, which is 0.1 L square over 12. Whoa. Divide. This is minus this one. Okay, guys, you need more space. Keep it. And likewise, same load over here. Basically, for now, as you know that the current let me put here, this stands for current U, which is all equals to 0. Then you come up with current force. This is the internal force, which is equal to the MMULT of this and this displacement. Here's to be, oh yeah, this is divided by L, so everything is dimensionless already. Okay. Work the same way for the other element. And this is just U3. Yeah, just copy. This is a pure force resistance. Alright, then we can this part here, when you set up the system of equilibrium, we are solving for the residual. We are solving for the displacement increment that correct the residual force between the apply, right, and the internal resistance. So to make it precise, let me just add, not add, will change from, yeah, there. Change from just U to delta U to be consistent with the node that we developed. But over there, the current U will be used to evaluate the internal forces. Right. This multiply EIOL multiplied by this all equal to force vector on the right hand side. Basically, this is the apply DOF loads, which is 0, and then minus apply span loads. So the span loads come from this plus this and this is equal to this one. And then minus resistance, which is determined from current U. So this resistance come from all the beam elements and also the spring. So from the beam, we have U3, U4, which is that current F. Good. You and then add up with this one, U3, U4, and U5, U6. Oh no. Let me just, current force is like this. Apply fixed span load. Okay. And what else? At the DOF 3, you also have the translational spring force that push up. Let me just reduce the so add up with the contribution from left spring, and this has nothing to help. This add up with contribution from the right spring. Let me get it okay down like that, plus not update this one also. I fixed it already. Plus the F here, and for the moment this has to add up with the moment from there. The thing is that, let's take a look at this a bit. The way we add the spring force back at this point here, spring force is opposite to the deformation. Okay, we had a lot of absolute thing going on there, so we need to put the sign of the spring force. So here for this one E21, which is this current spring force, I will put the sign. It has to be minus the sign of the U. Alright, so when we take the displacement and stuff it in there, please also put the sign. Due to the architecture that I make over here, I have to put the sign of the displacement, such that when it comes to this point, it will be taken care of correctly. If the support settle down, then we expect the force to push that node up. So plus it back, because the spring is the resistant force, or okay, if it works this way, then the spring, where is it? Spring resistance if it's not too nonlinear, then we get the chance to come back, but okay, no spring resistance, you get this one, you update this, you get this, and then calculate spring resistance, drop it in, you get this one, get this one is equals to this plus the from previous step, doesn't need to change. Okay, so if we compare this with this, okay, not much change, so we have a chance to be within that limit. Okay, yeah, but yes, thank you. So spring is already the resistance, which is in the same direction as the apply external force. So yeah, I shouldn't put the minus sign in there. Then we have to come back in here. This one has to change to from minus to plus. Okay, but I need to update this first. So this displacement solution is used to update here. Okay, and the U3, U4 will come down to here, and the U3 is going to update this one. U4, where is it? This one, right? Oh, this is be U5 coming here. Alright, to do this. Okay. And this to this one. Basically, it should make it like saying that you this is U what? U5, right? Current theta or current U6. Yeah. Current U4. So we update all of them. You have the new beam force and the new spring forces. Okay. Update, get the new solution, which is over here. So you can consider this. This is the right hand side. No. This is the residual. Okay, the total residual you have, which is the difference between external force and internal force now. If you consider the first step, the residual is 0.1, 0.05, 0.83. The second step, residual came down. The third step, residual came to here. If you want to continue, make the last one should be just enough. Number 4. So number 4, we will take this information from 3 that was already updated, put it here. These 2 has to come down in here. No, sorry. It has to be. Hey, oh yes. Oh, okay, here. And then the number 4. This is number 3, right? Not 4. And number 5 in place. Number 6 put in place. Why? Is there anything? I mean, it should supposed to converge. What is in here in this? Where is it? J. Okay. It doesn't change from before. Why is it? 1,6 and then come down to 1,4. Okay, let's see. Is it 1,6, 1,4, 1,2, 1,2, 009? I think for the okay, first step 1,4, second 1,6. It shouldn't swing. It shouldn't swing so much. It gets softened, I guess. And then here it come back to 1,6 again, right? I think the formula is self-contained already. We do not have to change anything. Why is it changed from? This is about 1,5, and then we solve. It come down. Solution is small. Right now, it changed. Hey, okay, got it. We didn't change this. We didn't change the formula in here. 1,4 still, right? So. Let's make it this one. Iteration 1, it doesn't really bother. Hey, iteration. Okay. It will be fast now. Number 1, you get this solution. Number 2, this is from there. Okay. make it the formula, and we will not have the headed later. So this, how do I make it like this? Previous step solution. Okay, nice. If we talk about the first one, then we put it here and it's all 0. So this is equal to this plus this, okay? Okay. Likewise for the number 2, okay, we have this one, and for this one, delete it. Yes. Okay, so this add up with this, you get this. And in the next step, we just but here we update, we got to put it here, okay. So we get the new one, I think we update, we use 0.14 in top here, right? And down here you get 0.16, 156, which we put it here already, so everything was updated. But the problem was just we didn't, the formula was tied up with number, it's not tied up with like something like this. So here we copy this into here from the previous step, and then this was updated from this number and this number, so okay, it doesn't swing that way anymore. It swing because we did it wrong. And then I get this and I paste there. Okay, and 0.157 come to here, 118 come to here, and 094 come to here. Then the convergence is nice, so the residual term has approached to 0, and the correction, okay, it's not fixed yet, so and this correction has to be coming from here, previous step, and this formulation. So, all right, okay, looks good. Oh, so now we get the solution. 0.0016, 0.0012. Lucky that 0016, 0012 are still here. I fix the axis. And this axis 04. Okay, so here is the straight line portion. Actually I should add the like 0.0011, yeah. Okay, nice. So the structure is somewhere around here. It has some softening, but it is not coming down like that. But the reason it came down like that, one thing, okay, the point Sivaram points out, the spring resistance, the sign was switched, so the residual calculation turns out to be wrong. And another thing is that the way I tied up the residual formula, the updated displacement, which I put the value and then add up with the displacement increment. So I copy that from the first sheet, and the displacement value at the original one is not changed, so convergence is not achieved. Alright, so now everything was all fixed, and yeah, this is a solution. The current case, okay, right, done. Next class we're gonna do the modified Newton-Raphson.